Hello, how's it going? In this video, we're going to generate a Bezier curve to sort of simulate a elastic surface that can deform over time. I tried to do a physical simulation, it didn't turn out so well, but it still looks pretty cool. Most important thing is we can set up a patch, a Bezier curve, and flash that over to the GPU dynamically to get things animated. So I suppose I should talk about sort of the setup that I'm going to go with. We have this scene, and this scene will have an elastic curve, a surface, an elastic surface, which is set up with two corners. Now what's happening is, if we look at this elastic surface, we interpolate a 4x4 grid along those corners. So if we have a region of space split into 4x4, we generate 16 control points. Now if we move these control points, the goal will be to interpolate a Bezier surface through those control points, cubic surface through those control points. So we set this up, and then the goal is to do a sort of semi-physical animation. So I've got velocities for each of these points, and in my update I sort of have two forces. I have a constant downward force of gravity, and then I sort of calculate the tension based on each of the neighbors. So the way this tension force is going to work is it's a spring force basically. So it's the other position minus our position. So for instance, if there is the other point is above us, then that difference should be positive, and the net force would be upwards. And that's pretty much all the net force is up or down, because it's completely symmetric and we're not introducing any sideways forces. Anyway, this has been a whole lot of rambling, but I'm just sort of laying this out. Also, these forces are only applied to the central points, the 4 points in the center of the grid. So the boundary points are sort of fixed in position. We could have animated those too. As a matter of fact, we could have animated all but a few of the points, then we'd have sort of a flag animation. But anyway, this is what I went with. So then, in addition to that, we had a dynamic curve class before. We also have a dynamic surface class, which pretty much works exactly the same way. The point is, it can take a bunch of data and send that into its vertex buffer object. But anyway, all of this code, as always, is in the description, and what I really want to focus on is the shader programming and getting the actual rendering done, because at the moment this stuff just exists, we're not really using it. So let's clear all of this off, and we'll go one step at a time, starting with the vertex. Okay, nothing too exciting. We just take the position and transform it appropriately. So we've got the vertex shader done. The next stage is we go to the tessellation control shader. Okay, so we are essentially setting the tessellation level, and we're being very boring. We're setting it uniformly. That's fine. So for instance, if I pass in 512, then every dimension is going to be split 512 across. That's a bit much, but yeah, there we have it. Okay, so the tessellation control shader will wait until it's taken 16 vertices, and then it will sort of call the tessellation evaluation shader, which we can go ahead and build. Okay, so here we are basically evaluating the Bernstein polynomials for a given value of t. We are going to have two independent Bernstein polynomials for each of the axes, u and v, each of the parameters, and these are essentially linear, well, they're essentially cubic. Yeah, they're a cubic binomial expansion. So we've got, what is this? I think it's 1.0 minus t to the power of 3. Something like that. Something like that. But essentially, you know, essentially we have a cubic... Just double checking there. Yeah, that's cubic. That's a binomial cubic expansion. Yep. Of these, and for our purposes, that's enough. But what we do need is we need the partial derivatives of the Bernstein polynomials as well, because the cross product of the partial derivatives will give us the normal. So in addition to evaluating these coefficients, we also need to evaluate their derivatives, which is simple enough. It's just the power rule. By the way I've set this up is we're taking in an argument b, but we're taking it with an out layout. So this sort of saves us the hassle of making temporary variables and then sending them out. Especially it helps us get around multiple return types, which we're doing here. But anyway, so we're going to get the derivative of the Bernstein polynomials by the power rule. So bring the power down and reduce the power by 1. And then by the chain rule, multiply by the derivative of 1.0 minus t, which is -1. So there we have that one. Now here we have the power rule, the product rule. So it's derivative of the first term and then derivative of the second term. So we're going to have two of these. And, all right, so power rule. Bring the power down by 1. So this is just the regular bracket, 1 minus t. So that multiplies, and then multiply by the derivative of -t, which is -1. And then this stuff can stay the same because the derivative of t is 1. So, yep, that is the second term. And then the rest of this is very similar. So take the derivative of that bracket, it goes away, it's just -1. Then take the derivative of t squared is 2t. And then finally take the derivative of t cubed is 3t squared. And I just spotted my own typo. For once. All right, cool. So we've got the Bernstein polynomials. Awesome. Now, this next bit is going to involve a lot of writing. So I'm actually going to paste it over from my notes because it's too much. You don't want to sit here and watch me type this. Jeez. Okay, so what are we doing? Well, first of all, we get the tessellation coordinate and we unpack the two components of it. This gives us our u and v parameters. Then also we unpack the patch. The patch will have 16 control points. We unpack each of them, and the way this is being denoted is the first index here is the u index, and the second is the v index. Fair enough. So then we evaluate the Bernstein polynomials in u and v, and then we use that information to fill in the position and the partial derivatives. So to get the position, we essentially take the point and multiply it by the corresponding Bernstein polynomial in each of its indices. So for instance, across this top row of the calculation, we are only varying the v, and so we only vary the Bernstein polynomial in v. For instance, what do we have? 2, 3 is u2 and b3, and then we just simply take the summation of all of that. Okay, and then similarly with the partial derivatives, we have the change in position with respect to u is essentially the same, but because it's with respect to u, we take the u partial for each of these evaluations. And then for the change in position with respect to v, we take the v partial for each of the evaluations. But, I mean, other than that, it's just a rule that we can apply. It works for a general Bezier curve of any type. It's fine. Okay, so we take the cross product of the normals of the partial derivatives. Now remember, a partial derivative is a direction which lies in the plane. So if I look at a curved surface and I look in the u partial derivative, that's saying as I step one step across the surface in the u direction, what happens to our height, essentially. The cross product of two vectors will produce a third vector which is normal to each of them, orthogonal to both of them. So if these two directional derivatives are tangent to the plane, then normal to both of that must be the normal vector. Anyway, we also set the fragment position to the GL position, so this is actually writing it out to the screen. And then based on the Tessellation shader's internal workings, this will stitch everything together into quads or triangles on the screen. So this is all well and good. A lot of fun, a lot of writing. Let's pop over and write the fragment shader. And actually, I think, let's take the, where is it? Fragment tune. Let's take the tune shader and adapt that. Okay, so point light, that's good. Fragment position, yeah, okay, let's go back and call that fragment position. Okay. Color, we're not going to do that. Normal, yes, 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 yes. Okay, now I'm going to take color as a uniform. Going to call that tint, just like I'm calling everything else tint. Silhouette color, we do not need that. Final color, yes. Calculate point light, yes. Okay, we can get rid of all this conditional statement here. We are not silhouetting the surface. Okay, and that is fine. I guess the only thing is here I'm actually taking in a four-dimensional vector, and that's just because it turned out a little easier for me because evaluating the Bernstein polynomials is annoying, so I only want to do it once, and I stored that result into the fragment position variable, so I could use it again to set the GL position. Yeah, there it is. So we just have to work around that. So what we'll do is cast this to a 3D vector from a 4D. And I think the rest of this is fine. Hello, we're back. I don't know what was happening with that. My mic lead is dodgy, but yep, there we are. We are back. We just need to set the tint instead of the fragment color. Okay, cool. So I think that is good. Fingers crossed. Now let's go to... Yeah, and just a reminder, this should be working just fine. It's just that we're not rendering it. So if I go to Scene, in my update, I am updating the surface. So if the surface has any sort of physics simulations on it, it's bouncing around on my RAM stick. I just need to render it. Okay, so what do we need to do? Well, we need to go to the engine and I need to set things up so that I have a shader. So I'm just going to bring this down here. Okay, so I've got my surface shader. Now I'll go to the source code and we'll just go through this. So yeah, let's get rid of that for now. Create shaders, so just grab this. Okay, so we've set those. We don't use a geometry shader, but the rest is fine. We have surface shader. Okay, good. Okay, so we've created that. Just don't forget to delete it as well. Okay, great. Now we'll need to get the shader locations. So before we get the shader locations, we should probably declare in our header file what shader locations we're going to have. So here we have, yeah, I'm happy with all of this. We're just going to need an extra light location, just because of the way this has been set up. So shader location is a standard struct, which will actually hold a whole bunch of these. So we'll put a field in here so we can register the location within the surface shader of whatever. And light location is sort of a composite data structure. So we have one of those for each shader that we're going to be working with, as you'd see from the previous videos. So now we'll go over to shader locations, and it's pretty similar to the toon shader actually. So we can just grab that. I guess we're just also going to have tint in there. So yeah, just reset this. Okay, so we're querying the surface shader for all of these, and we'll store the result as the surface field. And we'll set these in the surface lights. Okay, unless I've done something egregious, which I'll find out later, or not. We'll leave that there. Now we'll set the one-time shader data. So what do we want to set? It's pretty similar to this one actually. So we're going to set the projection transform once, and I'm also going to set, I called that detail. So yeah, let's stick with 40 for now. So 40 tessellation levels on the surface, that looks okay. Create models, so I'm going to need to make something here as well. I've got a dynamic curve, I'm going to need a dynamic surface. Okay, so I will also have, where is it? A surface mesh, okay, good. Then let's create that. Okay, right. And of course, don't forget to destroy it. It's the old, you know, create something, destroy it. Okay, cool. Righty. So that is done. Create models is fine. Create materials, render. All right. So things are going to change a little bit because I'm making my Bezier curve, and that has a patch size of 4 because I want to send in 4 control points at a time. So I'll set that there. But then when I create my Bezier surface, I'm going to use different parameters. So let's see. Surface shader. Patch vertices are now 16 because we have a 4x4 grid. Set the view transform. Set the model transform to the identity because I'm tracking those things myself in my code. And then set the tint. And this is scene. What is it? Surface color. It's going to complain. Well, it should complain because I'm actually setting a 3-dimensional color here. Okay, so I'll go build my surface mesh based on the surface control points. Okay, just a whole lot of fun here. And finally, when I go to draw, I'm drawing GL patches, 16 points. So let's run this and see what it does. Oh no, let's just do it and see what happens. We'll fix it up later. Okay, so that's not so great. We got something. But yeah, that's not great. It's a little bit weird. I think what we need to do is disable backface culling. Here's the thing, I'm sort of lazy. If I can get away with it, I'll just never have backface culling. Because oh, okay. No, that's not good. That is not good. Okay, let's see. Oh, okay, no, that's fine. Okay. Undefined variable fragment color. It's probably in the fragment shader. Yeah. Just go tint. And see how that goes. There we go. Okay. That's looking better. I wonder why it's so dark though. What am I thinking? Okay. Pop quiz. Pop quiz. Let me know if you know why it's dark. Okay. So it is doing the elastic stuff. That's pretty cool. It's dark because I didn't send the light data. Jeez. Sometimes I surprise myself. Okay, so I'll just go back up here where we're looping through the lights and send that in. I think that's all right. Okay. What's it complaining about? Okay, there we go. We got it. It's lighting. It's doing toon shading. That's nice. It's very cool. And yeah. Anyway, I'm really happy with that. Let me show you. So at the moment, I'm splitting each dimension 40 ways, and that's happening on the GPU. I actually looked up what are these Bezier surfaces used for? And somebody said online, it's when you play Hitman and you see his round head, his bald head. That's what they use the GPU for. But anyway, so where was I? Set the one-time data. At the moment, we're doing 40 subdivisions. We can do 4 and see what that looks like as well. Hint, it looks not as good. But if we're rendering from a distance, this could be a good way to implement level of detail. Because we're passing this in dynamically. And we can also set it based on calculations in the GPU. But let's set it to a crazy value. There's probably no point to do this much, but 1024 subdivisions in each dimension. And I mean, honestly, looks pretty similar to 40, but the number's bigger. Anyway, we can get a lot of detail, and all we're doing is passing in 16 points. So I think that's cool. Anyway, I hope this has been fun. I know it's been a while since I've put a video up, like a whole week. I've been really busy, but yeah, I was wanting to put videos up the whole time. Anyway, I hope you had fun. I hope you enjoyed this session, and I'll see you again soon. Bye.